I'm going to introduce the people in the room, and I'm going to turn my virtual off, my virtual background. There we go. This is where I'm actually sitting. And I'm going to turn something else off, which is what's going on in my background. There we go. Okay. So let's see how we're going to do this. Lara, should I log to the VNC and share my screen that way? Would that be? I'm going to do that. Okay. So we're going to, hey, Vicky. Hi, Maxim. We're going to wait for just another minute. I'm going to start sharing my screen in just a couple of minutes. How are you, Vicky?
Hello.
Hi.
Let me try that without mute. Wonderful having you on Molokai.
Oh, it was such a pleasure. Such a pleasure.
Thank you so much.
What number DEIMOS are we? DEIMOS 8, okay. And is it okay if I go into, should I go into view only or allow controls? What do you think? Okay. Okay. I may not be able to do that anyway from here because of the way the buttons work, but I'll go in without view only, and then if necessary, I'll go. DEIMOS 8, you said? Hey, you think we're just starting a chat at the scientist session, so okay, I'm going to share my screen, folks, and let's see if that works. You should be able to see my screen now, and it is, there's actually not one, but 1, 2, 3, 4 different screens that we use to control the telescope and instrument. This is something called, this screen is called Control 0. Yeah, welcome everyone. I am going to turn off my chat for a moment. So this is called Control 0, the screen. And the top bar here. Let's see if I can find it. Yeah, you see the words Control 0 written where my cursor is. So that's Control 0. This is Control 1. This is Control 2. And this one is called Tel status, meaning telescope status. You'll see that written at the top of the screen. So with this screen, we monitor the status of the telescope, where it's pointed, sky conditions as well. And the first 3 windows, this one, Control 0, 1, 2, they control the instrument that takes the light from the telescope and measures various things about the stars. Okay, so I see something in the chat. Yeah, thank you, Jamika. Thanks for. Yeah, so I'm sitting on the Big Island of Hawaii, but not on the summit of Maunakea. I can see the summit of Maunakea ahead of me. I'm at Maunakea is at 14,000 feet. I'm sitting here at Shelley. What is the altitude of Waimea? Is it like altitude 2,500? Okay, yeah. So we are much closer to sea level than Maunakea. Okay, so that's what we're doing now. if you're looking at, I'm going to bring up, give me a moment, I'm going to bring a metal plate to hold in front of you. I'm going to stop my sharing for a moment. Yeah, we're using metal plates like this one to collect a spectra of something like close to 200 stars at once. If you look closely here, you'll see there are multiple cuts in this piece of metal. This particular plate is not for our experiment, of course. The plates that we're using for our experiment are actually on the mountain on Maunakea. This one has relatively long cuts. These slits are quite long, and there's about 100 of them across this. The mask we're using has closer to 200, 180, 190 of these slits. Each one of these slits is allowing us to measure the spectrum of a different star. These are, of course, stars that are close together on the sky. When this metal plate, the length of the metal plate, that is the distance between my arms, that corresponds to the radius of the full moon. That's how big a patch of sky it is. It's the radius of the full moon, not the diameter, the radius of the full moon. So it's 16 arc minutes, or about a quarter of 1 degree. The full moon's diameter is half a degree, its radius is a quarter of a degree. So that gives you a sense of how much of the sky, how much of Andromeda can be accessed in one go simultaneously with this telescope and spectrograph. And in that patch of sky, there are thousands of stars, of course, but we are getting spectra of, well, several tens, several hundreds of thousands of stars in Andromeda within that patch of the sky, but we're only getting spectra of a bright subset, about 200 of them. Okay, let me take a moment here to see if there are, if I can introduce Sunny, Shelley, McConaughey, John. We have visitors in our observing room here in Hawaii. And so I wanted to introduce them in person. I'm going to take my headset off for this. Vicky, let me bring Sunny to you. Just a moment. I'm going to take my Sunny, Vicky's going to say hi to you.
Okay.
Oh,
Hey there, Sunny. How's it? Did you guys happen? Were you on the same flight?
Huh?
Were you and Raja on the same flight?
Just introduce yourself, please.
Folks,
How's it?
Community Relations Coordinator over here. Hi, Rita. Yeah, Rob.
Rob
Hey, guys.
connects from many times.
Oh,
Thank you
awesome.
for welcoming Sunny. Thank you so much.
So Vicky is Sunny's school teacher in Molokai.
Oh, right
And I was
on.
just there yesterday with the two of them in Molokai.
Oh, look. Oh, you traveling back. Oh, right on.
And then, Rob, if you want to take a moment to introduce yourself. Sorry, I didn't mean to. Rob, if you want to take a moment to introduce yourself, and Maxim will have you do that after Rob. Rob, go ahead, please.
Okay, I'm an amateur astronomer. I was introduced to this program through the Griffith Observatory. I work at UCLA. And I've attended a lot of these which I really enjoy the program.
Thank you, Rob.
Outstanding.
So, Griffith Observatory is in the hills near the Hollywood sign in Southern California.
Okay, you see it.
One of my close to it. One of my former PhD students helps run the planetarium show there. So they featured Shadow the Scientist in one of their programs one year. That's how Rob got connected to us.
Oh, right on.
And Maxim, do you have a moment to introduce yourself? Please go ahead.
The same. I'm an amateur astronomer.
You presented your program about a year ago to SVIS community here in Sacramento Valley, and I'm just from time to time joining and enjoy to look what you're doing, how you're doing.
Welcome.
Awesome.
Thank you.
Wow, for staying up so late, you folks.
Yeah.
California, yeah?
Yeah, it's 11 o'clock. Yeah. So I gave a talk at the Sacramento Valley Astronomical Association. So that's where that's how my accent found out about
Okay.
this thing. Oh, thank you. Thank you for connecting.
Outstanding. Yeah, I'd like to learn a lot more about like the
I
program
would love that.
and be a part of it as well. You know, maybe help the students from both organizations.
I'd love that. I'm here through, I'm leaving on Tuesday morning. So maybe
Okay.
I'm happy to come chat with you if you have
I'll
time.
be at Astro Day tomorrow.
Okay, me too. Me too. I'll be there. I'll be there.
Awesome.
I'll be there all day. So we can chat.
All right. Yeah. There's all of the different organizations as well. So
Jamaica will be there as well. I'll be helping Jamaica at the Shadow of the Scientist table. So we'll have all the materials there. We can
Okay.
absolutely.
we can have Roger get all the cards for everyone down there from all of the telescopes and have everybody connect with each other.
That's wonderful.
Yeah, make like a big upena, a big net. Capture everyone together.
You know, we really are trying to get other astronomers to host sessions. You know, our group has been hosting sessions for a while, but we really want to make research a spectator sport. You know, we watch soccer on TV, we watch cricket on TV, we watch actors, we watch movie stars, but no one watches scientists. So this is the chance to do that.
Right?
Yeah.
It's exciting.
Just to
you know,
demystify-
get people interested as well, because if you
Get
don't
people
have an
interested.
avenue,
Yeah,
people won't know what's available.
exactly. We want to demystify.
Right, right.
What is it like to be a professional engineer? What is it like to be a professional astronomer,
Exactly.
artist? So we're trying to get other professions to shadow, to host the shadow sessions.
Right.
Next month, I think we'll expand to biology, I think next month. So
Wow.
we'll see,
Awesome. You know, we got OTEC down here, Nelha,
Okay.
Natural Energy Labs.
Oh,
all
yeah.
that.
That would be
You
amazing.
know, science
That
is
would-
science. We're
that-
all studying.
That would be
Nothing
amazing.
specifically.
I would love to get the, you know, so there's right next to the Natural Energy Lab is the world's largest seahorse farm. Literally the world's largest seahorse farm. I've been there once with my wife and daughter. I would love to, you know, if with their permission, go around and, you know, have someone shadow the work they do.
Right.
And, you know, kids would be so interested in that. You know, this is something that seahorses are mythical, mysterious creatures. I would love to get NEC or I think I forget what they're called, but they're the world's largest seahorse farm.
Wow.
They're amazing. Actually, they're right next to the airport and right next to the NEC.
We have a big abalone farm. We have lobsters down there. We have, like, it's expanded so much now. My son was working at the shrimp farm,
I see.
SIS, Shrimp Industry System,
I see.
and they don't sell shrimp. They sell breeders,
I see.
right? So like they ship this certain type of breed of shrimp out to the rest of the world, like from right here. So
Same thing for their seahorse farm. They are sending it to aquariums around the world. There are some parts of the world where they use for medicinal purposes. So it's incredible. There were seahorses that were that big. There were seahorses that were that tiny. And you could put your finger in there. They would wrap your tail around your. They were
I thought you were gonna tell me you were riding a snow. Ride some sauces.
I wish they're not that big.
Well, definitely want to connect.
I'd love
For
that.
sure, right?
I'd love that. If you're around,
And then
and
if we can connect with each other as well, you know.
I'll do that.
Victoria, Maxim, Rob.
I'll absolutely do that. We have a mailing list of everyone who connects to our Shadow the Scientist session.
Right,
Thank
if you
you.
can
Thank you.
share with them my
I will
information, if
absolutely
you'd
do
like.
that. Thank you. I'll share it with Jamaica first. She's our coordinator and then she has the whole mailing list. Thank you. Thank you.
Oh, no worries. Yeah, I'm so sorry. I've been packing up the boxes. I'm sweating.
No. And you know, Keck has been a pioneer in this. We started with Keck and Lick, and I'm hoping other telescopes will follow.
We can.
It-
We just gotta get the attention, right?
Yeah,
We have to be that squeaky wheel.
yeah,
The squeaky wheel always gets the oil.
yeah.
So
That's
we just mix up those together. But definitely, Raja, I'll see you tomorrow.
I'll see you. Take
For
care.
sure.
That's today, definitely. And then
Yes.
we make a plan to chat then and also on Monday.
For sure.
Take care. Thanks for stuff.
Oh, anytime. I'm all for your time, folks.
Of course, of course, of course.
And then hopefully tomorrow, son. If not, My cell phone mama call me up, we talk stories sometimes. Okay, folks, take care.
So I'm going to go back to sharing my screen where I wanted to stop sharing while we were introducing one another. Vicky, you didn't get a chance to introduce yourself, but I will certainly connect you to he is the, Kekoa is the community relations coordinator for Keck Observatory. And of course, Shadow is such a great way of connecting the observatory, not just the scientists, but the observatory to the community. So Keck has taken a strong interest in this, and Shelley, of course, is a big part of that. So I'll share my screen and we can see what's going on tonight. So when I was showing this metal plate, you may have noticed that these slits are very narrow. They're very, very narrow, and we have to make sure the telescope is pointed just right. Otherwise, the star that we're interested in won't shine through the slit. So to achieve very good alignment of the telescope and perfect rotation, we cut these boxes, these square boxes into the metal plate, and they are aligned with faint by our human eye standards, but bright by the standards of the Keck telescope. We connect the boxes are aligned with relatively bright stars in the sky, bright for the Keck telescope, faint for a human eye. And so then we make sure that the stars are right at the center of the box. And that's what you're seeing on the screen here. You can see the image of a star, and it's pretty much centered, maybe slightly to the right of center. That's what you're also seeing on the screen up here. We're actually making detailed measurements of how far it is off center. And we have not one, but multiple boxes. So let me close this, and you'll see that we have so star 1, 2, 3, 4, 5, 6. If I scroll down, you'll see that there is a total of 8 stars. And these peaks are, I'm going to put on my headset so you can hear me a little better. For each of these boxes, we don't judge by eye whether the star is centered or not. Instead, we have some software that first collapses all the light in the vertical direction and looks at where is the peak in X. That's what this graph is. Then it does the same thing, but collapses all the columns and says, where is the peak in Y? And it tries to fit, you see a dotted red line here, look very faintly. That's the computer's best guess for where the center of the star is in X and Y for each of the stars. There's 8 stars, 8 boxes. It does that for each of them. And you can imagine that these boxes, you can see a pattern here. 3 of the boxes are at one side. 5 of the boxes, 1, 2, 3, 4, 5 are on the right side. 3 of them are on the left side. Now, if the telescope is off by a certain amount, all the stars, their peaks will be left of center, just like you're seeing here. They're all slightly left of center in the X direction. In the Y direction, they're more or less centered, right? You can see all of them, but actually not all. On the left, so stars 4, 5, 6, 7, 8, they're all off to one side in X. Stars 1, 2, 3, they're all off to the right side. So stars 1, 2, 3 are over here. Stars 4, 5, 6, 7, 8 are over here. They're offset in opposite directions. That means the telescope needs the instrument needs a little bit of rotation. So this is, we figured out how much X offset there is, how much Y offset there is, how much rotation there is. I don't say we, an algorithm figures it out, and until the telescope is perfectly aligned. So that's what this is doing. But this entire window is sort of devoted to that. In this window, we get to see the first set of spectra that came out. And you'll notice that there are these 8 rectangles. They're numbered 1, 2, 3, 4, 5, 6, 7, 8. Number 5 stopped working a few days ago. It came back to life yesterday. Tonight it's not working again. It means we lose some of our data, some of the spectra, because the spectra run vertically. So we lose half the spectrum for 1/4 of the stars. Okay. The stars are, the spectra of the stars are, as you can see, they're vertical rows like this. So for half the stars, we'll lose, sorry, for 1/4 of the stars, for 25% of the stars, we'll lose half their spectrum. We might still be able to measure a velocity. We might still be able to extract useful information. They're not completely lost, but this is an example of an instrumental breakdown. This is something that this instrument has been struggling with for the last 4 years. We're trying to revamp the instrument, trying to improve it. Hey, Michael, I was just noticing that, yeah, CCD5 is still completely dead. Yeah, so the CCDs, they're called charge coupled devices. They're numbered 1, 2, 3, 4 across the bottom, 5, 6, 7, 8 across the top. And 1 and 5 collect spectra of the same stars. The blue part of the spectrum, short wavelength part of the spectrum on CCD1, the red part of the spectrum, long wavelength part of the spectrum on CCD5. Same thing for 2 and 6, 3 and 7, 4 and 8. These pairs of charge coupled devices, pairs of silicon devices, they collect spectra. So I'm going to zoom in on this a little bit, just to see how, yeah, and you can see that with a little bit of imagination, actually with a little bit of scrutiny, not imagination, you can see that every one of these has a faint or in some cases obvious vertical stripe down the middle. This is the light of a star. I'm going to change the, Michael, I've forgotten how to change the stretch. Let me see. I'm just trying to check on how we can. Michael, how do I control the contrast and brightness on Ginga? I've forgotten. Oh, right click. You know, with because I'm on BNC, I don't think I can. I can try to do it from the screen there. I'm just trying to increase contrast. Oh, there you go. Can we go to slightly high, even higher? Yeah, okay, this is perfect. Thank you. A little higher contrast and a little darker, maybe. Oh, this is perfect. Yeah, thank you. So you can see that for the folks on Zoom, you can see that there's a very bright star down the middle of this slit, or down the right side of the slit. This one has a relatively bright star. This one has a bright star. This is a single 20-minute exposure with Keck. Here's, this one's faint, but you can see it. With a little bit of imagination, you can see the one on this one as well. And if I change which part I'm looking at, if I zoom out. You can see that you know, pretty much every slit has a vertical, sometimes faint, sometimes bright vertical streak going through it. And the reason some are faint, some are bright is some of the stars are bright, some of the stars are faint, and we study a variety of stars of different brightnesses, different stars in the Andromeda galaxy. All of these stars are in the Andromeda galaxy. I should say most are. They're in the direction of Andromeda. Some turn out to be in the foreground. Some turn out to be other things, galaxies or quasars in the background. That happens sometimes. These these horizontal bars that you're seeing here, these are produced by the glow of the Earth's atmosphere. The Earth's atmosphere is particularly active at these long red wavelengths. So in the you can see already from this display that these bars are much more prominent in the upper part at longer wavelengths than at shorter wavelengths. If I go here, you don't see many of them. You go up here, you see quite a few of them. Again, up here, lots, down here, very few. So this very bright line over here, let me see if I can zoom in a little. This very bright line here, this is in the green part of the spectrum, and this is the same process that's produced by oxygen. It's the same green light that one sees in the northern lights and southern lights in Aurora Australis, Australia Borealis. But all of these horizontal lines are produced by the Earth's atmosphere. We are not interested in them. We need to remove them so that we can study the spectrum of the thing that is running vertically, which is the spectrum of a star in Andromeda. The really bright ones, in fact, here's something really cool you can see right there. I'm going to zoom in on this. Let's see if I can. I'm going to zoom in. Lara, look at the calcium triplet on this thing. Can you see the calcium triplet, Lara, on that thing? On the bright star. You can really see the calcium triplet there. So these gaps that you see, folks, in the spectrum, these are produced by calcium. They're produced by not calcium atoms, but calcium ions that end up absorbing light of certain wavelengths. You can see another absorption right up there. You can barely see it. You see a break in that spectrum. So the strongest of the calcium triplet dips is this one. And I can show you what that looks like in a 1D spectrum. Let me see if I can find that in a 1D spectrum. See if I can find them here. Yeah. Let me see if I can find one for you. So you see these three dips over here in the spectrum. That's produced by calcium ions. And this is what you're seeing in front of you, something called a 1D spectrum, one-dimensional spectrum, where you have the color of light or wavelength on the x-axis and how much energy is coming out of each wavelength. And what we were seeing earlier is something called a 2D spectrum, and a two-dimensional spectrum where wavelength is increasing upwards. And those are the three dips, calcium triplet dips. You'll notice that the first two are close together. Third one is far away. You can see already looking at this that this middle one is the deepest. The break looks most prominent there. It's least prominent for the first one, most prominent for the middle one. So shortest wavelength one is least prominent, middle one is the most prominent. Again, I'll go back to the 1D spectrum, and you can see that the middle one is the deepest. The right one is almost as deep, but the one on the left, shortest wavelength one, is the weakest. This is produced by calcium ions. Okay. Take care, Michael. All right. I've been talking for a bit. Any questions from the group? I'm going to keep sharing my screen so I can. So Lara's actually explaining something that I will.
So as a 2D spectrum and 1D spectrum are slightly different. So it's a negative version of one of another.
No, you know the difference. That's a great question. The difference between a 2D and 1D spectrum is we extract the 2D. We first create a 2D spectrum where what you've got is we are taking a spectrum of a slit, right? Of a slit. So every point in the slit creates a spectrum. That's why it's 2D, because the slit is one-dimensional. It's a long line. Every part of the slit creates a spectrum. So you get a 2D spectrum where the vertical axis, or in this case, you saw the 2D spectrum where the horizontal axis was where you are along the slit, and the vertical axis was wavelength. From that, we collapse it. We collapse all the columns and create a 1D spectrum from that. So the 2D spectrum is sort of an intermediate step to extracting a 1D spectrum.
But on 2D, you see kind of emission lines, and 1D spectra is absorptions.
No, 2D
spectrum.
was also absorption. I'll show you.
Just negative version. I mean,
No. So this is 2D. These are absorption. See? Oh, you mean these vertical lines? These emission lines are produced by the Earth's atmosphere. For the star, it's only absorption lines. It's these three absorption lines: 1, 2, and 3. Yeah, they're both absorption. Now, depending on what you study, some objects, some astronomical objects do have emission lines, like galaxies have emission lines, nebulae have emission lines. But the stars we are studying, most of the time, not all the time, most of the time they have absorption lines. Occasionally, they'll have emission lines when the star is undergoing a flare. For example, in the sun, if you look at the main body of the sun, you get absorption lines. But if you look at the solar corona, you see emission lines. So sometimes stars have a very prominent corona, so prominent that that's what's dominating, and then the light, and then you see emission lines even from stars. Very rare, but you sometimes see them.
Okay. Yeah. Thank you.
Sure, of course. Other questions? I know we have a small crowd today, but other questions? So I will show you a different screen in a second. Okay, excellent. We're going to do a mask alignment next. Oh, perfect. Okay, so Lara's going to align a mask. Take it away, Lara. So controls are all yours. I'm just. So Lara's got the controls. And the mask we observed was for, yep. We're moving the telescope now to a slightly different patch of sky. It should be in the star list file, yes.
You're doing alignment to a new target, or it's just because of it's
we are going to observe a different mask,
a
different metal plate. So slightly different patch of sky, different orientation. That's what Rita was asking about. PA is position angle, the angle of the camera, and this rectangle that I'm holding up here, exactly how it's oriented. You know, PA0 would be like that, but not running north-south. And PA90 would be running east-west and so on. So they're so we know beforehand when we design these masks what the rough position angle, what the rough sky coordinates will be. So we're not moving the telescope very far because all of these masks we're observing are in a certain region of the Andromeda galaxy, in the same region of the Andromeda. So we're not moving we're moving less than 1 degree in the sky, less than half the diameter of the full moon. Sorry, less than, yeah.
So it's not related to alignment for it's a Keck telescope. It's alt-azimuth telescope, correct?
It's an alt-azimuth telescope, exactly.
Okay, so you need to rotate your
exactly.
Okay.
Yeah, you have to rotate. That's right. Once the telescope, once the alignment of the mask is complete and it's locked in, you're right. The instrument is constantly rotating to keep the sky fixed in the reference frame of the detectors, of the silicon detectors. Or if this were a photographic plate, it would keep the image frozen in the field of the photographic plate. Of course, we're using digital device here.
Plate itself rotated, not a telescope rotated.
What is being rotated is the spectrograph. It's shaped like a cylinder, and the whole spectrograph.
Okay. Makes sense.
It's a giant cylinder. It's the size of a small room, but the cylinder, it's shaped like a cylinder, so it can rotate on its axis.
So at least it's less than 10 meters of Keck.
Yes,
Yeah,
yes.
main
Everything scales
mirror.
up though. Yeah, when the mirror is that big, the instruments are, you know,
Yeah.
it's, I've sat inside the spectrograph, so it's it's a few meters in length and maybe 1.5 meters in diameter. So you know, a human being can crawl inside that.
Thank you.
I'm going to show you the screen that Shelley is talking about. No, good. I'm sure. Basically, the telescope is rotating equal and opposite to the Earth's rotation. So if the Earth is rotating like this, the telescope has to rotate like that, exactly equal and opposite to that. So it's pointed at one. Yeah. You know, it's like saying if I'm spinning my my chair, but I want to keep looking at you, my head has to keep turning while you know, it's exactly like that. Yeah. Okay, so they're doing this alignment of the mask that's happening in this window. So you'll see these. It says CD readout. Oh, you know what? I'm going to share my screen with sound so you can hear the telescope sounds. I'm going to reshare my screen this time with sound. So these boxes, in a moment, it's finished reading out the image, is now analyzing the image. And as soon as it's done, it'll put up plots in these boxes, one in each of these black squares. It's analyzing the image, right, Lara and Michael? Oh, good. Okay, no problem.
Exposure complete. DCD readout complete.
That's many stars. That's 1 million stars, that image. That's not a single one. It's a collection of 1 million stars. There we go. Oh, wow. This is beautiful. Lara, the seeing is so good. Look at how peaky. I'm going to measure the seeing.
Right wall that at it.
That's 1 billion stars. The collection of 1 million stars. It's called a globular cluster. It has a name. It's Messier 5 M5 1 million. Yeah. Hello, who just joined? Hey, Rohit. It's good to see you, young man. How are you? Yes. Rohit, how are you? Can you hear me?
Yes, I can hear you. Thank you.
Sorry. I should have been in view only, Lara. But the seeing is spectacular. I'm going to measure the seeing. The seeing is fantastic. Did you measure the seeing for the last one? No.
The seeing is
That's
about
okay.
0.7
on the guider,
0.7.
which
Okay,
is
I'm
actually,
going to,
that's worse
or-
than it really is, right?
it's slightly worse, but I'm going to measure it on these. I can steal the cursor now? Okay, so I'm going to measure seeing here. How do I
Yeah,
do
you'll
it?
get a better
Interactive.
value.
Interactive, right? I want interactive. Seeing. Okay, there we go. Oh, look at how beautiful these images are. Beautiful, beautiful, beautiful. So I'm going to do P for photometry. No, R for radial profile. There we go. Beautiful. Wow. So full width half maximum 5.7. That is about 0.7 arc seconds. So then it shows the next one. This is one of the, so if for each of these boxes, we can do this analysis. This one has 1, 2, 3, 4, 5, 6, 7. Ours, the one we're actually using, has 8. And we can make this measurement for each of them. Ooh.
One was there, that has it as well, so just have her call me. Otherwise, I'll jump on.
Yeah. Thanks, man.
Yeah, I'll see it. I might just connect from home. That's okay. Carlos is going up with an instrument technician. So they're gonna like swap from hardware up. So that was the thing.
Oh, Carlos is going to go up to the summit? Wow. Wow. That's very good of him.
Probably 4 again.
So for those of you on Zoom, you can see 5.88 over here. That's the full width half maximum of the seeing in pixels. So I'm going to multiply that by the pixel scale. So 5.88 multiplied by 0.1185. So that's 0.7 arc second seeing. It's quite good.
Yeah, and then just email me the setup as well. Just to make sure you get it.
So that's actually good to know that the seeing that you measured is pretty close to the guider seeing, so you can
0.7 is
almost
what I'm
use them
measuring, yeah.
interchangeably.
Yeah,
At least
yeah,
for now.
and the images look as is, not uncommon. They look a little extended in X. I'm just looking at our compass rose. Let me see. Compass rose is telling me that the X direction is the elevation direction. So we're probably seeing something like atmospheric dispersion. That's why this thing is stretched out like that. I'm guessing that. But I mean, the X direction is east-west. So that means this mask must be a 90-degree mask, roughly, the PA. Right, Rita, what is the PA of this mask? Oh, I should know. I should be able to see
It
this
looks
thing.
like the PA for this one is 270. So
270, okay, so which is same as
90
90.
degrees off there. I think
Yeah.
that's exactly what you said, right?
Yeah, so east-west is horizontal, but I'm also seeing this compass rose that says the elevation axis is more or less horizontal. And when we're at such high air mass, we're at pretty high air mass right now, what happens is the atmospheric dispersion, meaning red and blue light go through are bent by different amounts by the Earth's atmosphere. So you get a slightly spread out image of the star. Yeah, we're at air mass of 1.45. So I imagine the seeing will get even better as the night progresses and Andromeda rises in the sky, and we're not looking through as much air. Look at how beautifully you can see the stars shining through the slit there. I'm going to zoom out a little bit. Look, there's a star shining through the slit here. There's a star shining through the slit there. Did you see that, you guys, on Zoom? There's another star shining through the slit. And we're looking at a very tiny patch of this whole frame. If I move to here, it's reassuring. This tells me that the mask is well aligned. That is, every time I have a slit, I'm seeing a star shining through the slit. And here's one of the boxes we were looking at earlier. You can get a sense of how this experiment is being done. We have a slit that's centered on a star. And of course, because this star is in Andromeda, it's not isolated. You can see fainter stars nearby that are also shining through the slit. These are just sort of chance stars that we're just catching by chance. I'll zoom out.
How you choose your target star? It's just bright enough, and
I'm sorry. I'm getting a question
yeah,
from.
sure.
So the way we choose our target stars is we first have a Hubble Space Telescope image of this part of the sky, and we do want the stars to be bright enough, but we also want them to be relatively isolated. That is, we don't want any other bright stars close to them, so that we can uniquely measure the spectrum of that star. Not uniquely, there's some contamination from neighbors, but if the neighbors are faint, then it's okay.
Okay, thank you.
So we use Hubble images, or if Hubble images are not available, we use images taken from the ground. Generally, for multi-object spectroscopy, you have to first take images, decide which of the objects, which of the light sources in your image you want to get a spectra of, and then design a mask, and then you're ready to do the experiment we're doing tonight.
Yeah, thank you.
Welcome, Stephen. Hi, Rohit. I don't know if you have a moment to say hello. Rohit, must be very late at night for you, or early morning for you.
Yes, early morning.
Early morning. Are you all settled in at Leeds?
Yep, thank you.
Very good, very good. Rohit was a mentor in the science internship program this past summer, and he worked on data like this, actually data on the Andromeda galaxy, spectra of stars, velocities of stars, working with that with 3 high school students, 1 from Kosovo, 1 from, and 2 from California? Right?
Yes.
No, yeah, and 1 student from India, right? 1 student, Stuti from India, Andrew, Tuana, who was your, who am I missing?
Akhil.
Tuana, Akhil was from California also. Akhil and Andrew from California, Tuana from Kosovo, and Stuti from India. And Lara was asking a question, so let me see if I can answer that question. They were asking about this screen over here that controls this right part of the screen that controls what is called flexure. I'm ready to explain. Okay, so what happens is when you have what is called an Altaz telescope. So what's an Altaz telescope versus an equatorial telescope? In the old days, when computers weren't so powerful, you built your telescope so that one of the axes was pointed towards the pole star. Okay, so when the sky rotates, you just rotate one of the motors. So you built the telescope in such a way that it points towards the poles. The one of the axes points towards the pole star, and so no matter where you're going in the sky, if you rotate around that axis, you can just track the sky. So you have to rotate only one motor, and much more difficult to rotate two motors. So if you have, that's called an equatorial mount. Those are much more expensive to build because you have to imagine the whole axis of the telescope has to be tilted so it's pointed towards the pole star. And in Hawaii, the pole star is only 19 degrees above the horizon. So it's a very tilted axis, load bearing, and all that becomes very complicated. So they started building telescopes when computers got more sophisticated, started building telescopes that are called Altaz telescopes. So one of the axes is how much you rotate like this, the other axis is up or down. So, but the problem is when the sky, when the Earth rotates and the sky appears to rotate equal and opposite to that, you have to move the telescope along both, you have to operate both motors at the same time and by exactly the right amount. Now, computers are very good at calculating all this, so they're able to do this. But when you have an Altaz telescope, see you, Shelley, see you tomorrow. When you have an Altaz telescope and you're trying to take an image of the sky appears to rotate within your frame. So if you have to actually rotate your camera equal to that. So the way we do this in this instrument is the instrument's shaped like a cylinder. We just rotate the axis of the cylinder in real time. It's rotating all the time, right? Because as long as you're taking an exposure, the cylinder is rotating. Now the cylinder is this huge thing. It's made of metal. It's literally the sizes from where I'm sitting to this wall. It's taller than I am. I've been inside this cylinder before when it was built in Santa Cruz. It was built on our campus. So this thing is heavy. It's got moving parts and it's not perfectly symmetric. There are spectrograph, there are lenses, there's a collimator mirror, there's a grating. There are heavy elements within that. And you can imagine that between when light enters this metal plate, one end of the spectrograph, and when light hits the silicon device, such a big thing could flex or bend slightly under its own weight. It does flex and bend slightly under its own weight when you rotate. That is the exact relationship between where light comes in and where light ends up. The exact spacing between them, the exact orientation between them can change under the weight of the whole spectrograph. So what you do is you move the silicon device left and right, up and down to compensate for that motion. That's what this thing on the right side is doing, sort of in a closed loop. Every time it moves slightly, it detects that. It says, okay, let me move the silicon device to the left. With moving to the right, then it says, okay, let me move to the right to catch up with it. So it has actually a range of motion that's fine. That's like does the fine correction. It has a range of motion that does the coarse correction. So it uses something called the tent mirror. It's using the grating tilt, and then finally it does the move. So these are amazingly sophisticated devices. The engineering behind it is just as rich and difficult and complex as the science. No, so this is one thing. This is true for not just for astronomy. It's true for biologists who use microscopes. The technology behind the instrument is a subject unto itself, and that technology is an enabling technology. So you can learn in biology. You're learning something about secrets of life, the secret of either human life or animal life. So biology, that's the target. Here we're trying to learn the secrets of the universe, but the enabling technology is a subject unto itself. I have colleagues whose entire research has to do with building better telescopes, building better spectrographs. In fact, the person who designed the Keck telescope was one of my colleagues at the University of California, Santa Cruz. There's the conference room that's named after him, Jerry Nelson. That's his name. He passed away several years ago. But it was his vision that you could build a telescope this size with mirror segments. It's sort of got a beehive shape to it. So that was his research. His entire research was, how do I build bigger, better, cheaper, more sustainable telescopes? And it's because of his research that so many other people are doing research with this telescope. So it's one of these beautiful synergies that you see a lot in science. one person's work enables another person's work. You know, I haven't seen that movie yet. Sunny says it reminds him of Oppenheimer. Andrew and Stephen on Zoom, if you have a chance, feel free to introduce yourselves. We haven't had a chance to hear from you.
Hi, yes, I'm Steve Pagano. I'm in Hawaii on Big Island. From my yard,
okay.
Yeah, from my yard, I could see the observatories on Maunakea.
Fantastic.
Mostly pretty clearly on a good day. And thanks for having me.
How did you find out about us? You're most welcome, of course. You're very welcome to these sessions. How did you find out about us? Was it through Hana Kilahoku?
Yeah, there's a lot of information on you guys locally, so it's you know, if you're looking for it, I guess you'll be able to find it, and I guess that's a good thing because it'd be great to see people.
I'm very happy to hear that. Very easy to find. That's good. I know there's a Jimmy had put a Facebook post as well for this particular session. Fantastic. Thank you for joining. And how about you, Andrew? Andrew, feel free to introduce yourself. Yeah, and actually, absolutely, I'm happy to send it to you. Vicky and Dara, of course, have all the details because we had two students from Maunakea in SIP last year, Azriel and Hunter. Others were interested also. At one point, I think Kai was thinking of applying. At one point, Kai was thinking of applying. So you were thinking of applying last year as well, I remember. So yeah, definitely the information there. What we're doing this year is we're actually, if you tell us what subject we're interested in, we've started something called precept. We were talking about it in school yesterday. Let's say a group of students says they're interested in astronomy. Sunny's not the only one. There's a few other students who've said we're interested in astronomy. Some students have said we're interested in animals, or either fish or animals. We're interested in that subject. Someone else might have said they're interested in engineering. We're going to group students into these different interest groups, and we'll give them some reading and viewing. So, for example, project that Azriel worked on last summer. High school students, including Azriel, what he worked on last summer was an astronomy project. And what we want the astronomy group to do is see some astronomy projects that were offered last summer through the eyes of high school students who did that project. So it'll be something that, they of course had to learn this stuff. And at the end of the summer, they had to present their work. We wanted to hear through them so you'll see two paragraphs that describe what the project is, the beginning of the summer, and then a 15-minute presentation that says what they did, why they did it, why was this important, what the technical challenges were. And your group, say you're part of the astronomy group, we'll ask you to write down, or we'll give you a third thing. So we'll give you these paragraphs of multiple astronomy projects, these presentations by high school students about what they did. We'll ask you to watch these and start making notes of things you don't understand. And things you do understand and find interesting, that's one side of the column. Other side, start making notes of things you don't understand. We also gave them papers to read, the papers that our group had already published. And those are very technical. So reading those, you get lots of material that you don't understand. So it'll be very easy to fill the left column. And we'll ask the students to do that. And then we'll meet with you by Zoom and say, okay, let's go through some of these questions. These are important questions. Let's try to understand them. The idea is to prepare you through the school year. So whatever subject you're passionate about, whether it's art or music or astronomy, you get some exposure to it, and then whether you apply to SIP or not, you have gained this experience. And if you are applying to SIP, it puts you at a huge advantage. That's what pre-SIP will do.
How long is it?
So this summer, the first 2 weeks were online because we don't have housing available on campus the first 2 weeks. So students did the work online, and then for the next 8 weeks, we had housing available. So I think Hunter and Azrael were both there for 8 weeks. Aria from Oahu was also there for 8 weeks. We may shorten the program a little bit. The online one, instead of doing 2 weeks, we'll probably do 1 week. And the housing, we may shorten it to as short as 6. So it might be 1 + 6, but the 1 would be online and the 6 would be in person. We may shorten it. I don't think we'd shorten it any more than 1 + 6. We're thinking of 1 + 6 or 1 + 7. 7 weeks in person or 6 weeks in person and 1 week online before. But there'll be flexibility if you can't stay there for all 6 weeks or all 7 weeks. If it's a 7-week program, you need to come back. Say school is starting. Of course, you know, you'll have that. School comes first. There's no question. So that's what we're thinking of the structure. We realize 2 + 8 is very long. Yeah. Of course. Please come. Please come. Please come. When Sunny comes, please come, because I know Azrael's parents came to drop him off, and I think he went back on his own, but they came to drop him off. I think Georgia came to drop Hunter off. Yeah. And we'd like to get Maunakea High School students involved as well. So this is not exclusive to Akaula. Obviously, this year we had 394 students in the program. Yeah, you have my email, of course, right? No, you don't. Okay, very good. Yeah, here's my phone number. Yeah, we've been texting today. We had 394 students in the program this summer. This is the 15th year of our program. First year, there were 3 students. Next year, there were 15 students. So we've been growing like that. 29 students the third year, 43 students the fourth year. This year, the 394 students. Of them, 91 students were international, came from different parts of the world. I mean, Azrael and Hunter will tell you, we had students from the Middle East, from Turkey, from Eastern Europe, from Africa, from Asia, Central America, South America. So we had kids from all over the world. We had 2 students from Australia. Many students did it completely online. We found that that's difficult because when you're completely online and your time zone is very different, very hard to engage. So we're trying to get students to come because I think the in-person experience is much better. You're on the campus. It's a beautiful campus. You're surrounded by redwoods. You'll see the ocean in front. You'll have a blast. You know? Of course. I totally understand. I think that'll put your heart at ease because you'll see that he's surrounded by warm and caring people, and I think that will be important. You please come. We would welcome you. Of course. I completely understand.
Go away.
Yeah. No, but please send Mokulele High School students to this program, and we'll get them started in this precept thing also. That's also for everyone. It's not just for Akaula. We are going to put together these subject groups so that students can start engaging with some of the material during that. I would do that in a heartbeat. Yeah.
I already know you want to go, so we'll yes. The answer is yes. But
It's 9, yeah. The KTA has been closed for an hour. You have. Okay. Yeah, I got up very early because Vicky brought me to the center of town, then Dara dropped me off to the airport, and there was like an exchange. And Angel came in the car with me. There's the school mascot. There's a dog who adopted the school, basically. Yeah. I didn't go this time. No, where it is, right next to the school, right? Yeah. I know exactly. You come out of the school, you turn left, and it's over there. Yeah. Thank you for coming. Thank you for coming. I really appreciate it. This room is the control center for the Keck II telescope. You see that arrow? It says you're here. In that room is the control center for the other telescope. There's the same picture, but the arrow pointing to the other. Yeah. So these are twin telescopes. When Jerry Nelson designed this, he said, if you build a second telescope, it's much cheaper because all the design work has already gone into one. You don't have to redo the design. Yeah. You came with the school, yeah. We should, and Keck, you heard from Tekoa, from Shelley. The observatory really wants to change that. They want to. I think people should see what's going on here. There's no mystery here, right? People should see what's going on. It's really impressive. What's happening is really impressive. I mean, this, yeah. I think you're most welcome. You're most welcome. This has become such a special place for me.
I'll start with you first before we go online and stuff like that.
Folks on Zoom, I'll be right back. I'm sorry for the silence. I'll be right back. Hi, folks, I'm back. Sorry about that. We had in-person visitors in the control room, and I was seeing them out. Our image quality has improved significantly since the first exposure, and I think you could see many of these slits contain a vertical streak through the center. And I think whenever you have good seeing, more of the light of the star is going through the slit. So you can really see that here. I'm impressed. Of course. Rob, are you still seeing this gray rectangle in the middle?
Yeah, it just went away, but I saw it for a little while.
Is it back now?
Yes, it is.
Okay. Every time I open the chat window to see what people are writing in the chat, that's what that is.
That's
Even
the
though
chat
I'm
window.
sharing my full screen, I'm not sharing one window. I'm sharing my full screen. It's still doing that. I'm not. I think I've seen
Yeah,
this
the
happen before.
the floating windows sometimes don't get. I see that.
You see that, right? Okay.
I see
Yeah,
that,
this is like my text window. I was deliberately testing with another window, so it is still sharing full screen. It's not sharing part of my
Mhm.
screen. Let me just close this. Sorry, but I think somehow this chat window is of course Zoom related. How about if I open participants? Do you see a gray screen, a gray rectangle now?
Yep.
You do. Okay. So I think anything that's Zoom related, it seems to get confused because this time, or maybe it's deliberate. It doesn't want everyone to see the chat just because I'm opening the chat, right? I think it might be a privacy thing because people
Could very well be.
They could direct message me, in which case I would see it. But if my screen share were on there, everyone would see it. It could be something to do with that.
Probably.
I think it's only the Zoom related windows that get grayed out here.
Okay, I wasn't sure if that was blocking some of what you were describing about the flexure stuff when
Flexure. Yeah, let me go to the flexure screen. This is the screen that controls flexure. Where is it? This screen over here. It's a super system. This is something that my colleague Sandy Faber designed the demograph, and she came up with this, and it's really brilliant. What we're trying to control is the following. If you have a star's spectrum, light of a star coming through a slit in a metal plate, if that star's spectrum is falling on, let's say, a particular wavelength of that star's spectrum, let's say the H alpha line, 6563, that particular wavelength, the goal is to have that land on a given pixel of the detector array and have that pixel not change in the course of the exposure as the instrument rotates and the gravity vector changes. So the bending of the instrument under its own weight is called flexure. Flexing, to flex is to bend. One can flex one's muscles, but in this case, flexure is a bad thing. It's causing the bending of the instrument. So what's being done here is at the ends of the metal plate, sort of in the fixed frame that holds this metal plate, there are three. Are there three or how many are there? I think it's two light fibers, one on the left side, one on the right side. And why am I seeing? Let me think about this. Is it? I think it's two light fibers at each end, and you shine sort of a copper arc through it, like a our copper arc lamp light shines through these light fibers. So they effectively become artificial stars that are shining all the time at the ends of the masks, beyond the ends of the mask, on two on either side. Now, because they are copper lamps, they produce arc lamps, they produce emission lines at very specific wavelengths. That's what you're seeing on these screens here. These dots, the white dots that you see in these 4 gray rectangles. I think the reason it's 4 rectangles is because we are looking at, not because it's 4 light fibers, because you can see that these are different wavelength ranges. You're seeing different, I think each light fiber, its spectrum is broken up into 2 parts, a red and a blue part, I think. That's what I think we're seeing on the left and right. And then the 2 fibers, one's below the other, you can see. And they're spatially offset from each other, so their arc lamp lines don't land exactly in the same, one spectrum, you'd have to slide one to match it up with the other, slide one horizontally to match it up with the other. And I don't know if I'm doing a very good job of explaining the orientation of this. So then what happens is these are not shining on the science CCDs, but they're shining on a special set of CCDs that are called for flexure compensation. And every time one of these copper arc lamp dots tries to move to the left or right because of flexure, the system corrects. It's a closed loop correction system. It's called the FCS, flexure compensation system. That's why you see FCS over here. And tracking means it's tracking. And just to give you a sense of how finely it's keeping things fixed, these units over here is pixels. So this entire box is half a pixel. And you can see that all of the centering is well within this box. The jitter that's happening as the telescope is, as the instrument is rotating and it's flexing and the system is trying to correct it. The correction is never perfect, but the amount of scatter is well within half a pixel, is well within a quarter of a pixel. That's the half side, or the half of this box is a quarter pixel. So the full box is a half pixel by a half pixel, and the amount of jitter is really tiny. There's more jitter along the X than along the Y. That's in the wavelength direction. There is more jitter than in the spatial direction. That seems to be typical for this. That has to do with how sensitive and how precise the compensation systems are in X versus Y. There have to be different compensation systems because one of the axes is wavelengths, one of the axes is spatial position along the slit. Anyway, that's a very quick explanation of FCS, flexure compensation system. And you can see it's, yeah.
Sort of sounds a little bit like an autoguider correction.
It's like an autoguider, very much like an autoguider, except it's not working in image space, it's working in spectrum space, in 2D spectrum space.
Right, yeah.
Yeah. I mean, in a way, an autoguider is also being, I mean, not in a way, an autoguider is also being used here. That's what you're seeing in this screen here. This is a guider. And here, this particular little rectangle, it's keeping whatever star is in that rectangle at the same coordinates to a fraction of a pixel. So it has to do that to make sure that the light of a star is still shining through the slit. So there's sort of 2 kinds of alignment that need to be maintained. One is as the telescope rotates to compensate for the rotation of the Earth, it has to make sure that that every slit is still collecting the light of the stars they were designed for, and that there's no drift. Because if there was a drift, then the light of the star for which the slit is designed, that light would hit the metal plate instead of the slit itself. So that part is happening here. Once the light enters the slit, because of the bending of the spectrograph, it would normally not land on the spectrum of that light would not land on the same set of pixels throughout the course of the exposure. That's what the FCS is correcting for. So it's sort of 2 compensations. One is to make sure that we're properly correcting for the rotation of the Earth. That's what's happening on this screen that you see here. That's the autoguider part. And the second part is the accounting for the bending of the spectrograph rotation as it rotates. Its gravity vector, gravity load changes, the thing flexes ever so slightly, and this system that you're about to see now on the right-hand side of the screen. That connects for the internal flexure.
Thanks for the explanation.
Sure. I don't think I've ever explained this to the group before. FCS is a difficult thing to explain. Yeah. A gray window must have popped up and now should be gone again. I have a little bit of a quiz question for our Zoom audience. I said that these horizontal bars are produced by the Earth's atmosphere, right? And you'll notice that in some cases, they're not horizontal bars. They look like horizontal, they don't look very thin. Look at this one. It looks like a little window, or it looks like a rectangle. Why do you think some look like these and some look like, are they all produced by the Earth's atmosphere? In fact, these two bright lines are the same as these two, same as these two, same as these two. Why do some of them look like these so chunky while others look thin like this? Most of them look thin. If I go here, for example, most of them look thin, but occasionally you come across things that look a little chunky, like this one is chunky. Or this one is chunky. This one's chunky, but the others are not. Again, you see the same pair of lines. These two are the same as these two, same as these two. And the reason they're offset is because, of course, the slits are cut at different parts of the metal. So the wavelength scale is shifted upwards or downwards depending on the location of the slit. All right. Anyone want to hazard a guess as to why some of the night sky emission lines look chunky like this? In some slits, in this slit, the night sky, all the lines look chunky like this. Look, they're all chunky. And this one, they're all narrow, all these others.
Diffraction on mirror? Your spider on mirror?
No, I'll give you a hint. I'll give you a hint. When you see night sky lines like this, they're actually repeated images of the slit, right? Because it's the Earth's atmosphere is shining uniformly into the slit. So you get images of the slit, just different wavelengths get mapped to different parts of the detector. When you don't have a slit, when you have an alignment box, a square, that's when you get these chunky things. So these spectra where you see this chunky looking emission lines from the Earth's atmosphere, they are the alignment boxes that we use to align the mask. We still get a spectrum through them. They don't look perfectly square, they look slightly rectangular, and that has to do with another subtle effect called anamorphic magnification. Right? The magnification along the X and Y axes are slightly different because we're dealing with a spectrograph, a grating, where the angle of incidence and the angle of diffraction are not equal, unlike a mirror where you preserve shapes. Spectrograph doesn't preserve shapes, and that's a subtle effect called anamorphic magnification. I'll put the words in the chat, but it's a very subtle thing for spectrographs. Anamorphic. morph, of course, means shape. So anamorphic is, sort of destruction of the shape. A square gets mapped into a rectangle. Anamorphic magnification or anamorphic magnification. Sometimes it's called anamorphic distortion. That's something that is a feature of most spectrograph. And the way you can see that is these chunks are not perfectly square. They're slightly rectangular. Well, they actually look like parallelograms. See them here as well. Why they're not perfectly horizontal and tilted has to do with distortion within the camera. That's also very common. You can see here they're tilted from upper left to lower right in the left edge of the frame. Upper left to slight tilt from upper left to lower right, whereas on the right edge of the frame, if I click over here, it's the other way, lower left to upper right. And this has to do with sort of a bow shape produced by distortion within the camera. In the middle, things are more or less horizontal. You could see that I've clicked right on the middle of the frame. Things are. Wow, this is one bright star. Lara, have you seen this star? I'm finding occasions where I think we were talking about this, where these bright stars were not even part of the catalog, so the system didn't even know they were there. But, probably saturated, yeah. We get beautiful spectra for them, of course. Rakesh, I noticed you just joined. Did you have any questions for us? Or maybe you joined a while back, I missed you. If you wanted to introduce yourself, please feel free to. I think the other person we would love to hear from is Andrew. If you want to introduce yourself, please do. And Lara, the M31 SPU was the mask for sure. Okay, fantastic. I'm glad we got that. And then I think we're getting even better quality data for SPB. And SPB means it's got hot stars on the mask, but it's the same location as S5 and 6. Okay, right, okay. Got it. We got, yeah. I think we got very good conditions right now. So I think we'll get good spectra here. Folks, if there are, there's not much going on at our end in the sense that this exposure, the one that we're on, is the, let's see, it's the second of 3? No. Third of 3, okay. Which window is that in? Yeah. Oh, okay. Next screen over meaning. Oh, okay. This one, DEIMOS screen. That's DEIMOS FCS control, must be a different one. Yeah, okay, sure, go ahead. I can't see it. I guess I'm sharing my screen, so I can't.
So it's not this one, it's one of the others.
One over, okay. Oh, that's why, okay.
That one.
This one, 3 of 3.
the one.
I see that. Perfect, okay, thanks. So we've got about 400 seconds to go on this one exposure. And then we'll align a new mask. That's what we'll do for a couple more masks before before the fun is over for us for the night. I mean, it's 9:30, so we'll have another, it's roughly 2.5 hours before our night is done. 2 hours and 40 minutes. One of the things you can see in these images are cosmic rays. These are these very bright spots. Streaks. Streaks when the particle came in sort of at grazing incidence and therefore released electrons from a set of neighboring pixels along its path. Streaks are not uncommon for cosmic rays. Yeah, generally these very long streaks are grazing incidents. Also, of course, depends on the energy of the cosmic ray. And so one of the main reasons why we do not a single exposure, but 3 20-minute exposures, because then we can do anti-coincidence and remove these cosmic rays because they've struck these pixels during this 20-minute set. They'll strike different pixels in general. Different cosmic rays will strike different pixels in the next 20 minutes. So by comparing and combining them, we get rid of the cosmic rays. Exquisite data quality. Right, folks, I think I'm gonna stop the recording. Stop sharing my screen first, and then I think I'll stop the recording for now. Happy to answer questions if you have any remaining questions, and otherwise I think I'll end this session a little bit early today. We'd set it up for 2 hours, but I don't think we'll go for 2. There's nothing, not much else that will be happening now.